Okay, students. Let me just... We can't get the microphones working up here, so I'm going to have to project. So try not to talk on top of me, okay? Because I don't have the microphones going. So I don't have extra power. All right, we have exam 1 coming up next Tuesday, a week from today. It'll be right here. All our midterms will be here in this room. Next time on Thursday lecture, we're going to be working on triangulation and parallax. And just to get you started, if you haven't already done so, start reading carefully now in chapter 19.1 and 19.2, because we'll be talking about today's stuff and chapter 19.1 and 19.2 on Thursday. And we're going to bring it all together so you can have a nice bundle of concepts for exam number 1. And I could tell you that the stuff that we're going to be talking about today, you're going to be seeing in your dreams, especially after exam 1. I mean, it's because we're talking about ellipses today. And I made some circles yesterday, last time, kind of mangy looking circles, but I'm going to try to do better on that. We're going to do some document cam work in a few minutes. But before we do that, I want to go over exam preparation and procedures. I want you to get your brain ready to think. As I always tell students, if you want to get an A on my exams, you can do it without having to do... last 2 rows clear, please. Move forward.
There are a lot of seats down here.
Yeah, buku seats. And on exam 1, we're going to probably even move you down, clear the last 3 rows. You know, getting an A might be, this is a basic class, so getting an A on an exam might not be bodaciously difficult, but acing it, yep, you're going to have to really work your you-know-what off to get 100%. But the way to do that and crush my exams is to think. And you won't know what I'm talking about now, especially you newbie freshmen, until you've seen my first exam. And then you'll know, oh, now I know what Dr. B said. Because you're going to be looking at problems that really force you to stop, read it carefully again, and think about it, and then read it carefully again, and then think about it some more, and then make a decision or make a calculation. All right? So make sure you do that. Now, we're going all topics from the first day, January 9th, lecture 1. We talked about spectra and stuff. All the way up to this Thursday, January 25th. And, of course, all the readings. And if you are not up to snuff, if you missed lecture 3, where I kind of outlined the basic readings heading into exam 1, go to YouTube, lecture 3, and about 8:50 you'll see a little list. And as well as most of the introduction that we talked about last week and the week before. Now, for the exam, the procedure is no cell phones. All right? That is verboten. It's forbidden. You must not even take it out. So you get in the classroom, front of the room, please. Yeah. You get to the classroom, just stow it, put it on silent, and mute it, and just stow it. You may not use it even for a calculation. All right. And if we see you using a calculator, or if we see you using a cell phone, we'll have people patrolling. If we see you using a cell phone, we're going to assume you're cheating, and then you'll fail the test, and maybe even be dismissed from UCF, which we've done in the past. So last 2 rows, no, you may not sit in the last 2 rows. Move forward somewhere. There's seats up in the front here. All right. So no cell phone for any reason. Just bring one of these calculators. If you have a calculator, you know, left over from 8th grade, and it has a square root key on it. Ding. That's good. That'll be work. You know, if you don't have a calculator, you'll be all right. You'll just have to do a little bit of multiplication, 6th grade style, you know, with a pencil and paper, division. So bring one of these. This one is the one that I have. I bought it for like $15 at Walmart. You know, you get them pretty cheap at the bookstore too. Number 2 pencil. Make it a good one. And bring a good eraser. Do not rely on the eraser that comes with the pencil, because I have found, and you newbie freshmen, you will find, if you're not wise, that eraser is sometimes like 7 years old by the time you buy it. So it's not soft at all. It's like a rock. And then when you try to erase an answer on the Scantron, you wear a hole in the Scantron. And then you got big troubles. All right, so you don't want to do that. So get one of these, you know, rectangular paint jobs you used in 2nd grade. All right, UCF Scantron, raspberry colored, the one with the Pegasus logo. There's a picture of it up there. And I have been told, I have never checked it, but if you go to the SGA office, 2nd floor of the Student Union, any day of the week, once a day, you can get a freebie. All right. Yeah. You what? Yeah, that's just the one end of it. Yeah, it's I don't have one, but it's about half a piece of paper regular paper divided longwise. Yeah. So this is just a fraction of it. Yeah. Because it shows the main stuff, you know, the PID and the test form, stuff like that, and the UCF logo. All right, so do that, and of course bring your iClicker too, and make sure that it is registered. All right, and I had a student come up before class, Dr. B, I just got my iClicker too, and he was on iClicker.com, and I had to put the chop on that. No, iClicker.com, no. Register it in web courses only. Otherwise, you won't be getting any points. You'll be clicking away, and you know the thing is, what you may not realize. Clicking, if you're on frequency DD, I'll pick up your clicks, but I may not know who you are. And you'll get the Go Nitro message if you're on frequency DD. Last 2 rows, come on, you know the rules. Move on out of there. All right, just move forward somewhere. There's seats up in here. Yeah, you may be on the right frequency, but if you're not registered, I don't know, you know, who you are from Adam. All right? And neither does the computer. So you're toast. So you just got to register, that's all. Now, on that score, let me go over some iClicker data. Last 2 rows, vacant. Move up to the front. Move on up to the front. Come on, there's seats up here. I just put up some iClicker data. You may have noticed it. It's down here towards the bottom of your grades page. It says L4 total 11818. All right. No, you may not sit in the last 2 rows. You may not sit in the last 2 rows. All right. Nobody may sit in the last 2 rows. All right. Yeah, no, I should put yellow cones. I will have to do something. I guess this is getting a little tiresome. All right, thanks for getting in here. Seats up here. Come on, let's just make yourself at home. Yeah, so it's down here, and it says L4 total. Now I'm going to show, and it's a number. It's something point something something. And no, you may not sit in the last 2 rows. I'm going to bring an air horn. And just try to mosey on in there. All right, it's a decimal number, something point something something, except for this guy has a -1, and I'll tell you what that means too. Okay, so the score that I uploaded and that you can look, it's down at the bottom of your grades page. Let's see if Let's see if this works. The score of your... Nice. I didn't have to yell at that guy. All right. Okay, so it encodes two specific data. Now, the first thing it encodes is how many you answered. And on Thursday last week, first day of official clicking, we had 3 questions. All right? So the first number on there, the whole number part, is how many you got answered. And then the decimal fraction part tells you how many that you answered correctly. So for instance, this score, some of you have this, 3.02. Some of you have 3.03. Some of you have 3.00. But 3.02, that means that you answered 3 questions. And on a day when you had 3 questions, that means you answered all of them. All right? 2 of them you answered correctly. All right? And and we're going to do a little clicker question. Make sure your clicker's ready. We're going to do them in a second. So just to remind you, the participation pointage comes from the number that you answer. So that's when you look at the whole number part, you'll... Yes. When you look at the whole number part, and just keep track of that, and I'll be keeping track of it too, that's where your participation pointage, out of 25, 25 points for a regular part of your grade, they come out of that number. And then the number correct leads to 4 bonus points at the end of the semester if you get 75% of all the questions correct. All right, so if you get a B, 75%, that's a B. So if you get a B on the clicker questions, from last Thursday all the way to the end of April, then you're going to get 4 bonus points. Just figure 4 bonus points on the final makes the final a little bit easier for me to get an A. Okay, think of it that way. All right, now I will post updates of this kind 5 or 6 times, maybe this semester. So that's every 2-3 weeks, maybe. And it'll be a roundup of how many you answered and how many you have correct. So you'll always be able to, kind of keep yourself squared away and up to date on what you are doing. Right? And you can look at last Thursday's. I mean, it's just one day, but I was basically just trying to upload from the software. So it's just doing an experimental upload. And by the way, if you have a -1 in anything on web courses, in my classes anyways, -1 signifies, in this case, we didn't get any clicks from you. Okay? And if you have, and let me also point out, the reason that I'm bringing everybody to the front and being such an annoying menace to navigation is the clickers don't really work really well from the back of the room, I found out. So we're trying to maximize the number of clicks that you get in. But if you're late, if you don't get your answer in by the time I get to 0 on the countdown, that might also be why you don't have 3.01. You might have 2.01 from Thursday. You didn't click fast enough. But if you have a -1, that means you're not registered or possibly you didn't use your clicker correctly or something like that. All right. Now, I want to go through a few examples with you on the iClicker, about the iClicker. All right, so here's question number 1. Your mythical roundup on February 31st comes in at 21.16. Okay, what does that mean? Now, here's the example that I just went over. All right, so read that carefully. Oh, did I say read carefully? Yes. Always read carefully, especially with my questions. All right. How do you interpret that? 20 seconds to vote. 10, 9, 8, 7, 6, 5, 4. And you know, you guys can, in lecture, you can ask your neighbor. Just, you know, you can interact with your neighbor. Is that right? Is it really C? Or something like that? C, good. Good, definitely. What, on an exam, no. But in class, lecture, yep, definitely. 5, 4, 3, 2, 1. Come on. 0. Ching. All right. You better display this. We got a little bit of. There's a little bit of difficulty here. As you can see, the answers are spread out. So let's just reinforce this. Let's take out the example, and this is the correct answer, B. And here's how you analyze it.
Yeah, it's also wrong. We should say 16 of them are right.
Oh!
There wasn't a correct answer.
Who? Tricked. You know why? You know, because I had this set up for my afternoon lecture, and I thought I had it all modified. All right, I'll give everybody.
I can't.
We'll give everybody points on that. Anyways, so, all right. So this is what happens sometimes when I get caught napping by my own students. Anyways, 21 questions. You answered 16 of them correct. All right, that's what that means. Yeah, 37. Yeah, so actually, so most of you did. No, it's not even. All right. Well, you know what I'll do? I'll just throw that. We can throw that question out. We can delete that one. We'll delete that question. All right, next one. This one is correct. Okay, 21.16. And there were actually 25 questions by February 31st. Oh, wait a minute. There's no February 31st this year.
There's never a February 31st.
Or in any other year. So that makes it a mythical date. All right, so coordinate and double check. And 21.16. Move towards the front. No.
Rounding.
Hold on a second. All right. Yeah, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, you guys got it right, 99%. Yeah, so that is the correct answer. And you know what? We're going to go past this next slide because, all right, here we go. Let's go to this one. Next question. Do you have 75%? Yes or no? I spent a huge amount of time with the afternoon lecture. I just pasted them over here. Messed it up. I'll have to double check my afternoon lecture. Okay, 10 seconds to vote. 10. Move to the front, please. Up to the front. Yeah, there's seats up here. Come on.
A bunch over here.
5, 4, 3, 2, 1, 0. Yeah, this one, the correct answer is no because 16 out of 25 is 64%. So So you don't have 75%. So now, just to point something out to you, if you get below 75% and it's still fairly early in the semester, you're not sunk. You just bear down and try to get as many as you can correct. And you'll nab those 4 bonus points, and hopefully that'll tide you over from a B to an A or from a C to a B, something nice like that. All right, now let's get back to Copernicus and his followers. We talked about Copernicus last time, and I finished. This is one of the last slides that we talked about, and this one is actually an important diagram from chapter 2. The whole controversy about, is the sun at the center of the is it a solar system or is it an Earth system? Is everything orbiting Earth? And you can't really tell just by looking at the stars and matching or measuring the motion of the planets, at least unless you have a telescope. And Aristotle and those guys back in those days said, you know, if we could see parallax, if the sun is moving around if the Earth is moving around the sun, then the stars should appear to shift. And they do. But the stars are so far away that the shift, what we call a parallax shift, between January and June, for instance, is really, really small. And so it's hard to see. But what they could have done, and were not able to do, is see the crescent phase of Venus. If Venus is really interior to Earth's orbit, and Mercury too, and if Sun is at the center, some of the ancient Greeks thought that the Sun was at the center. It wasn't, Copernicus didn't come up with that idea. He just kind of brought it back and worked it out a little bit more detail, and he felt it was better. But they thought this, but guys like Aristotle and the geocentric crowd said if it's really sun-centered, if it's really heliocentric, we ought to see the crescent phase of Venus. All right, so here's the crescent phase, and here's where's my cursor? Here we go. Right in here, this would be new Venus. In other words, you don't see it. And we just can't, our moon right now is crescent, and so I think it's right here. I think this is the crescent moon that we see right now. And here's half Venus. Here's gibbous Venus. That means it's a whole Venus minus a crescent. All right. Gibbous moon is a full moon minus a crescent. All right. And symmetric left and right. But they couldn't see that. And even this guy, Tycho Brahe, who was the best and the last of the great naked eye astronomers, you can't make out parallax, stellar parallax. You can't make out the phases of Venus without a telescope. And the stellar parallax, you have to have a really good telescope. Now, Galileo's the one with his very, very low-power telescope, still better than a naked eye. He was able to see the phases of Venus. So that locked the heliocentric system in place for most people. And then in 1800s, they measured parallax, and that locked it in for everybody else. But Tycho Brahe was, he was trying. And he was also not the most mathematical guy. I mean, he was good for making measurements and observations and keeping records, but he wasn't. Like a lot of people, that wasn't his strong suit. But he faced a question that we still grapple with in this our day. And that is, how do you get better eyes on the universe? We're constantly developing new ways to observe and more precise ways to observe. You know, for instance, the Hubble Space Telescope, and something that's in orbit now but is defunct, the Hipparcos satellite. And we got a bunch of satellites, like the Gaia satellite is up there, and it's measuring stellar parallax. It's measuring that June to January shift of stars way far out, you know, halfway across the galaxy. It's amazing what the Gaia satellite, did you realize that? It's way out there. The Gaia satellite is. So, that, you know, a lot of people think, those guys, they didn't know what they're talking about. But really, if you think like they did, they were trying their best to get the most precise and the most abundant observations. Now, toward the end of his life, Tycho Brahe moved from Denmark over to Prague in the Austro-Hungarian Empire. And when he did, he found a young assistant named Johannes Kepler. And there's a picture of Johannes a little bit later. And he grew a beard and fancy clothes and stuff like that. Looks kind of like Shakespeare, right? So that's about the time, about the time that Shakespeare was writing plays and sonnets and stuff like that. Julius Caesar, forsooth, poor Yorick, I knew him well, and all that stuff. Kepler was trying to digest Brahe's numbers. And so in the rise of science in the West, Kepler is the one, he's the playmaker. He makes the play. And much as I hate it, the Jaguars lost to the hateful Cheatriots. In the fourth quarter, the Cheatriots did make plays, and the Jags did not. We'll get them next year, those buzzards. Jeez, Tom Brady. Anyway, so Kepler's the playmaker, and he was able to take all of, after Brahe died, he had all this data, all these measurements, and he was like one of these guys that, he just chews it up and digests it, and by God, he saw ellipses. He found discrepancies in the measurements. Tycho Brahe didn't pick it up, but Kepler did. He worked the math out and stuff, and he was looking at Mars, and he just couldn't get it to work out to a circle. It didn't add up. Just think of it that way. And here's the thing that he wrote in his memoirs. If I had believed that we could ignore these 8 minutes of arc in the orbit of Mars, I would have patched up my hypothesis accordingly. In other words, stay with circles, just like Copernicus and Tycho Brahe. But since it was not permissible to ignore those 8 minutes, pointed the road to a complete reformation in astronomy. And my wonderful students, another way of saying this is the numbers do the talking. If you're in a scientific activity, the scientific enterprise, your numbers have got to do the talking. And either they're for the good or they're for the bad. But if the numbers don't agree with what you observe, you got to do some splaining, or you got to do some modification. If everything lines up, then your theory is righteous. And so Kepler had to adjust his theory. Actually this was his key discovery, that the planetary orbits are actually ellipses, and it started with Mars because Mars has a fairly eccentric orbit. It's I shouldn't say very, but it's the least circular of the planets, its orbit. And Earth's orbit is actually elliptical slightly. It's not a perfect circle. Now, let me give you a side note about degrees and stuff. I just mentioned 8 minutes of arc. Okay, now, so put this over to the side. Just a little bit of refresher from 7th grade or what have you. One full circle, 360 degrees. Ding. Everybody knows that, I think. But you didn't know that this traces back to the Sumerians and the Babylonians and those guys. You know, so the Tigris and Euphrates River and all that stuff. They based their numbering, for whatever reason, on the number 6. So 6, 12, 60, 60 minutes in an hour, yeah, that traces back to those guys. 360 degrees in the sky, yeah, it traces back to those guys. And it correlates fairly nicely to the fact that we have 365 days in a year, you know, sun to sun. 1 full degree is subdivided into 60 minutes of arc. So a 60th of a degree. All right. And the full moon is about 30 arc minutes. It's about half a degree. And hey, you guys, the full moon is a half a degree roundabout. Whether it looks big, you know, the harvest moon looks orangey yellow, and you know it's down in the autumn, and you see it rising and stuff. And yeah, it's actually a little bit bigger at certain parts of the year, but not by much. It's still about a half a degree. It just looks big because you can see all the other stuff by the horizon to compare to it. But when it's up in the sky, it's the same. It's the same size. It's about half a degree. It just doesn't look like it. Your eyes play little tricks on you. Your visual resolution, unless you're like Superman or Wonder Woman, it's about 1 arc minute. All right, and you know, so that's about as fine as you can see by naked eye. Although Tycho Brahe was able to measure it, he didn't savvy those 8 minutes, but Kepler did. All right, so 1 minute of arc. Now we're eventually going to be working in seconds of arc and fractions of a second of arc, milli-arc seconds. 1 minute of arc is 60 arc seconds. All right, and so we'll be talking about arc seconds and milli-arc seconds all through the semester. You know, because when we measure the orbits of stars orbiting another star, yeah, we'll definitely be talking about milli-arc seconds. Question?
Can you go more into like the subsection 2? Like, what do you mean the full moon is equal to 30 arc minutes? Like, that's just... if you take a protractor and sight from the left edge of the moon to the right edge of the moon with a protractor, it's not even a degree. It seems, I mean, it seems small, but to your eye, it's big, you know. So for the moon to go from one horizon directly overhead to the other horizon, it crosses its own diameter. It's 180 degrees of motion, 360 diameters. All right, so 360. So that means that in 12 hours, let's see, 12 hours, you could work it out how many degrees the moon moves in every minute, and how many it moves in an hour, you know, based on that. Another question. Okay, now this idea of ellipses is extremely important, and you're going to think that I have an obsession with ellipses, but believe me, it's not me. It's Kepler, and it is me. Here's a kind of a cool movie. This shows you how you can draw an ellipse. If you have 2 thumbtacks or 2 fingertips of your friend and a piece of string, you can trace out the moving point would be the tip of your pencil, and you can just move it. And here's another image of it. So the thing with ellipses, we're going to go into all these parts here. You know, this major axis, the minor axis, semi-major axis, focus. He found it, you know, those are all like landmarks in geometry class for
ellipses. Now, I learned about ellipses when I was in 10th grade geometry class. And we'll learn about them today. And what he found was that not only are they geometric, but they're also physical dynamic meaning for like the focus and the semi-major axis of an ellipse. So let's go into his 3 laws of planetary motion. This is 3.1 now. All right. So this is the famous move. Kepler found that Mars had an elliptical orbit. And he said, and the sun is not at the center of the ellipse. He said it's at the focus. Now, the focus of an ellipse is not the same as the center. The focus is slightly off-center. There's 2 of them. All right, so let's look at an ellipse. Okay, so go ahead and draw yourself an ellipse. And the major axis is the long axis right down through the middle. So try to make it look symmetric. All right, and symbolically we'll refer to the length of that line segment as 2a. Right. The minor axis is this baby. All right, the short, and so they're going to form a plus sign or a cross, rectangular. They're perpendicular to each other. And yeah, the minor axis is the shorter one. And so if for this one, the minor axis is vertical. But if you're looking at a star in the sky, it can be tilted any direction. So, but it's going to have a minor axis. When you map out the star or the planet's orbit, the comet. Now this one, you can make a note. This one I measured really carefully. A is 300 pixels, B is 200 pixels, so the overall width and height are 600 and 400. All right. The quantity A is called the semi-major axis. Major axis is 2A, half of that is A, and so A is the symbol for half the major axis, or the one word we use it for it, the one phrase we use is semi-major axis. A semi-major axis is 300 pixels in my Apple Keynote software, and the semi-minor axis, B, is 200 pixels. So the total height is 400, the total width is, for this one, is 600. All right. There are 2 focal points and a center. Now the center is where the major and the minor axes cross. Okay, they're symmetric about the center. Okay, and they're perpendicular. The 2 focus points, or foci, are off center. Now this one, I mapped out the center very carefully. Or the focus. Here's one of them. All right, kind of eyeball it in. It's not at the center. It's not close to the center. It's a fairly eccentric ellipse. In other words, it's kind of oblong. Now the other one is symmetrically placed over here. All right, so they're the same distance left and right. They're on the major axis, and they're the same distance from the center. So they're symmetric on the semi-major axis, or excuse me, on the major axis. All right, and I didn't map out, put a dot for the center, but you can see that for yourself. Now, Kepler said the sun is going to be at one of the focuses of the ellipse. All right, and I'm going to just say, all right, for this comet, we'll just call this focus the sun's location. All right, and the other focus is empty. It's a geometric point, but physically it doesn't have a physical meaning. All right, so it's like a remnant of the mathematics. All right, now the distance from F1 out to the ellipse and back to F2 is a constant, and it's equal to 2a. It's equal to the major axis length. All right, and here's an example. If you go from F1 out to the ellipse and then back down to F2 on this dotted line, that distance is equal to 2a. right? And if you remember that animated thing, when you run the circle, when you run the pencil around the ellipse, you know, between the, you know, the two thumbtacks or the two fingertips of your friend, yeah, it applies to any point on the ellipse. I chose this one up at the very top, but you know, you could do the same thing. Choose a point like right over here, you know, at about 1 o'clock, right here where my cursor is, and draw the line segments and then add them, you know, measure the line segments, add them up, and they'll add up to the same number. Right? So it doesn't matter where you try to connect to it. So the distance from F1 up to the ellipse, anywhere on the ellipse, and then back down to F2 is 600 pixels. All right? Now, another property of an ellipse is its eccentricity. And this is pretty important for us, because this is the one that measures or that encodes the oblongness or the eccentricity, the departure from being a perfect circle. All right, so for this particular one, it's 0.745. Now we're going to do some clicker questions in a second using that number, so make sure you write that down. Okay, there's circumference, you can calculate. There's an area, it's particularly easy to calculate. Circumference is tricky, but area is, you know, the area of a circle, pi r squared. Area of an ellipse, pi ab. Ding. Circumference is tricky, though, very tricky. The closest point on the orbit is called perihelion. All right? That's an astronomy term. That's this one right here. So if the sun is right here at this focus, here's perihelion. That's where it's closest. All right? And it also happens to correspond to the point where it's moving the fastest. That's another thing that Kepler figured out. And over here, this is its far point on the orbits. This is way out there. It's called aphelion. All right? That's from, para is from the Greek word for above, periscope. Perihelion is the point above the, you know, close to the planet. Aphelion is from the word apo, away, from which common word is apostle. Those are sent. So aphelion means away from the sun. So that's the part farthest away from the sun. Right now, if you're talking about something orbiting Earth, and this could be a spacecraft orbit around the Earth. You know, they have eccentric orbits around the Earth. You would call it perigee and apogee. GEE referring to geo, Earth. But you don't call it apogeo, you call it apogee. So that's the terrestrial terminology. And, you know, there's various versions of the same idea, furthest point and nearest point. But those are some important ones. All right. Now, last thing to mention about the ellipse is it's supposedly symmetric. All right. Left and right, up and down. In this sketch anyways. All right. Now, sometimes when we're looking at, we're tracking a star in the sky, it's not perfectly, you know, north and south, east and west. You know, but you can still figure out the symmetry axes. So make a note, symmetry axes, you know, the semi-major axis, or the major axis, and the minor axis are symmetry axes. Now, I want you to hit the refresh key. And we're going to do a short answer. And actually, close that. Change that to multiple choice. This is I want you to think carefully about this question. You know, the previous ellipse, here it is. That one had an eccentricity of 0.745. Okay, now perfect circle. What's your guess? Exactly 1, exactly 0, infinity, or exactly 0.50, 1/2. And go ahead and talk with your neighbors. Think with your neighbors. It's very good. I see everybody pointing and talking about stuff. Yeah, so this one on the right is 0.745. And it's got more width than it does height. And the eccentricity ratio is 0.7. And I'm going to show you how to calculate here in a minute. All right, 15 seconds to vote. 15. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Good. 199 people voted. A true circle has 0 eccentricity, no eccentricity, so it's exactly 0. Now, go ahead and jot down this formula. Most of you got it right, actually. Here's the formula for the eccentricity. Go ahead and write this down. We're going to do some calculations with it. It's kind of tricky. It's a big square root, and inside the square root is a subtraction. And one of the things that's subtracted is a ratio, and the ratio numerator is the square of the semi-minor axis, and the ratio denominator is the square of the semi-major axis. But the thing that you may not realize is that for a circle is actually an ellipse with A and B exactly the same. All right? It's a circle is a special case of an ellipse. Semi-major and semi-minor axis exactly the same. Therefore, A over B is equal to 1. A squared over B squared, whatever they are, you square them and divide them. If they're equal, you get 1. 1 minus 1 is 0. So the eccentricity for a perfect circle is 0. Now, we're going to do some more calculations, but before we do that, make sure you have this equation jotted down. We're going to go over to the document cam and do a couple sample calculations of eccentricity. All right, so let me pause the recording here. And can you turn on the dot cam and bring up the lights to maximum? Let me get my cursor. Where's my cursor? Here we go. Here we go. Another question. This one's multiple choice. And I'll just park the sun over here this time. This one's 3 by 5, so it's a little bit different. And definitely kibitz with your neighbor if you feel like it. Double check your calculation stuff.
If I turn off the pen, will it save things?
Yeah.
Okay.
Just
I didn't want to just like.
you can turn it off. It'll turn itself off.
Okay.
Thank you for doing that. Let's just get ready to get out of here. I always hate it when I'm still getting my stuff put away and the next instructor comes in. I'm always embarrassed by that. Okay. 30 seconds. We'll give him till 2 minutes. Take your hand off the button, just like in Hawaii. Did you see that?
No.
They had some guy. He activated the nuclear missile alert out in Hawaii because he pressed the wrong button twice or something. And all these people are in a panic.
Yeah, that would be too.
And he didn't get fired. He should have faced a firing squad. All right, so this is a simple calculation. All right, 15 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. 199, come on. Too late. Go ahead and show them this results. Yeah, you guys are geniuses. Okay, back to the laptop, please. 95% of you got it correct. But if you didn't get it correct, here's how you do it. You plug in 3 and 5, square them inside the square root. And that's 9 over 25. Now, this one is pretty nice because you have 25 over 25 for your common denominators move, and then that gives you 16 over 25. And top and bottom are both easy square roots, 4 and 5 for the denominator. So this one's kind of cinchy. So there's your answer. 4/5 or 0.8. And just so you know, we're not done with lecture, but to let you know, homework 3 is activated. It's ready to go right after lecture, I think at 10:20. And it basically is just calculating eccentricities. So you'll have, I think I set it to 10 attempts. So just give it a couple shots. It's actually the orbital parameters I gave you are close to near-Earth asteroids. In other words, there's near-Earth asteroids with similar orbital dimensions. All right, now I have a visual IQ test for you, so hit your refresh key. This one is short answer. Okay. So hit the refresh key on your iClicker. All right. Otherwise, you won't be able to get the right answer here. All right. And this one I want you to grade every one. Now on this one, it's kind of a survey. So I'm going to give everybody correct on this one. All right. But give me your eyeball's best shot. Which is a perfect circle? When we close after this, I want you to go in and delete those first 2 questions that we screwed up on, okay? Okay, 15 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Come on, baby, get in your answer. Stop slacking. 0. Show them this. All right, now look at that. Everybody's got a different opinion, a significant number, 15, 19, 35, and 31%, and none of the options had a majority. Go back to the slide. The correct answer is... Now, so if you voted for Orbit 88, you could call yourself a genius for the day. Orbit K, this is actually, you're gonna want to make notes on this, but you're gonna have to look. Orbit K, this is the one that Kepler spotted. That's Mars. And most of you guys couldn't tell that apart from a perfect circle, but Kepler did. So here's the comparison, okay? I just moved them over to the side. Now, I want you to do this, add notes somehow if you can. You can't really make precise sketches, but your eyes can learn. Right. The perfect circle is the yellow one. So if it's a perfect circle, it's going to fit perfectly into a perfect square. All right, so that's what I got here. All right. Now let me copy that and park it over behind Mars's orbit. There it goes. See that little bit of daylight down there? Oh my goodness. Most of you guys didn't notice, but if you voted for K, you get the Kepler Award for today. All right? Because that's what Kepler spotted. All right. Let's keep going. Here's Kepler's, this is a diagram from chapter 3.1, figure 4, second law that Kepler worked out. And there's a lot to this. It's dynamical. In other words, it's not just the shape. It's the speeds that the planet orbits. A planet moves around its orbit. It sweeps out equal areas at equal times. Now, what that means is at perihelion, it is really moving fast. And at aphelion, it's pretty pokey. Because gravity's weaker out there. The further you get away from the sun, the weaker gravity gets. Everybody knows that. All right? But closer, you get stronger gravity, and you're really, it's like, you know, like when you're, if you've ever been on the roller skating rink or ice skating rink, and you do crack the whip. We used to do that when I was a kid. You know, and you crack the whip, you really start flying. The guy at the end of the whip, he really starts to fly. So over here at perihelion is fastest. Slowest over here at aphelion. And you put a dot down here somewhere, you know, at intermediate distance. That'll be somewhere between fastest and slowest. So that'd be a medium speed. All right? Now, here are some of the eccentricities and then minimum speed and maximum speed. This you can write down. Make a little table. We're going to do Earth, the Moon, and Mars. And I want you to compare the speeds. Now, the eccentricity of Earth's orbit around the Sun is 0.0167. Our minimum speed at aphelion is 29.29 kilometers per second. That's really going fast. Our maximum speed at perihelion, we're just barely closer. So it's exactly 1 kilometer per hour, or 1 kilometer per second faster, 30.29. Now the moon is a little bit more eccentric. Okay, so the moon is actually, when the moon is closer to Earth, it's, you know, it's fairly elliptic, the orbit. So but the orbital speed for the moon is a little bit slower, 0.970 kilometers per second, which is pretty fast, and versus maximum speed 1.082. And you can see there's a little bit more variation. The bigger the eccentricity, the more the variation between min and max speeds. So when you have a lot of eccentricity, you're going to have really fast at perihelion and really slow motion at aphelion. Now the example to really see that with is Mars. The eccentricity of Mars, you guys couldn't spot it, most of you, but Kepler spotted it. It's 0.0935. All right? And here are the orbital speeds for Mars. At farthest approach, aphelion, 21.97. But at perihelion, 26.5. And you know, the interesting thing is, this actually has the eccentricity of Mars, its orbit, has an effect on its seasons. It has some bodacious weather on Mars. They have huge global dust storms because of the weather, because of the eccentricity of the orbit. So here's what it means. Equal areas, equal times. This kind of pie-shaped wedge over here, over by perihelion, it's a lot of degrees, the angle, it's a lot of degrees, but the distance out to the orbit is not very far. So it's a different size piece of pie. But now over here, the same amount of time, you know, so like 30 days or 2 hours or whatever you want to call it, this slice of the pie is way different. It's much sliverier. It's only a couple degrees, all right, at aphelion. And it only subtends a small portion of the orbit, but it's really long, all right? So it's the same area. And Kepler, I have no idea how he figured it out. I don't even know. I don't even know how to do it with calculus. He didn't even have calculus. Newton invented calculus. Kepler didn't have any calculus. And it would be a tough problem to do this with a calculus. But he figured it out. It's amazing, actually. So these are 30-day periods. Now, if it were a perfect circle, then each 30-day period would sweep out an equal size and shape slice of pie. Right? That'd be like a pie that you buy at the store, you know. But this kind of a orbit, yeah, it's sliced up into slivery slices of pie and big honking pieces of pie. Now, I'm going to dismiss. You have homework 3. Next time we'll talk about Kepler's third law, the best of all 3. You're dismissed. I'll see you on Thursday. Turn the lights up 100%.
Slide with the eccentricities, like all 3 of them. I just didn't get Mars. Cool, thanks.
Hey, Doctor. I missed a lecture on Thursday because I was really sick with the flu, and I was wondering, like, is there anything I need to make up? And, like, do I need to send you, like, my doctor's note or whatever?
No, you just got to try not to miss any more lecture.
Okay.
Everybody's got, like, 1 or 2 lectures, 2 or 3 lectures to burn. Because you get full participation if you answer 85% of the questions.
Okay. So I'm still good. Appreciate it. Thank you.
No, you got to have the kind with the display screen. iClicker 2. Yeah. Did you already buy that?
From an online school, so I've like never had to use one of these before.
See if you can.
And I ordered it from Amazon.
Those jerks. Yeah, they don't. You should. You know what you should have done? You should have gone to the bookstore and look at what they got. Then go buy that same thing from Amazon. Yeah, iClicker 2. It's the one with the display screen. Can you send that back to Amazon?
I mean, I hope so. But,
I mean, they're pretty good about returns and
when
stuff.
I registered it, like it said it was registered.
Well, registering it is not a problem, but being able to do everything that, you know, like typing in a number, you're not going to be able to do with that.
The square sign. The square sign.
I guess we'll try to overnight.
Yeah, try to work it out. I probably picked up a bunch of your clicks, but I won't be getting your numbers, and I won't be you know, like the one where you guessed about Kepler's orbits and stuff. You might not have. I might not have gotten your click for that. So you're probably not totally. I'm probably not totally blind, but you definitely want to get iClicker 2, because on exam day, next Tuesday, definitely, you're gonna be SOL, yeah, on exam day. All right, good.
But then, like at the end,
Hey.
I don't even know how to use it. Like, let's go square root of something over.